Good morning. I am Dr. Jyoti Kumar. Today we will discuss about the topic syntax analyzer. Syntax analyzer is a second phase of compiler. It's a second phase of compiler. We can call syntax analyzer as a parser. Here, syntax analyzer creates a syntactic structure of a given source program, and syntax analyzer structure is mostly a parse tree. And as mentioned, syntax analyzer is also known as a parser. The main thing is the syntax of a programming is described by a context-free grammar. We will use Backus norm form notation in the description of CFG. Syntax analyzer or a parser check whether the given source program satisfies the rules implied by the context-free grammar or not. This is the most important point for a syntax analyzer. We are giving a statement. We are going to give an input string to a particular parser or a syntax analyzer, and the syntax analyzer is going to validate the particular source program or a particular set of string or a string, and it find out whether the given string is valid or not. If the given string is valid, then it is going for the next phase. If the string is not valid, it throws an error. And we have a context-free grammar. It gives a previous syntactic specification of a programming language. The design of a grammar is an initial phase of a design of a compiler. A grammar can be directly converted to a parser by some tools. We have parsing techniques. We have top-down parsing technique as well as bottom-up parsing technique. In top-down parsing technique, we have a recursive descent parsing, predictive parsing, and LLF1 parsing. On bottom-up parsing technique, we have operator presence parsing, shift radius parsing, and LR parsing. Again, LR is given to three types: a simple LR, canonical LR, and a look-ahead LR. This is a parser. Here we have a lexical analyzer. The input is a source program. The output is a token. The token is given to a parser. If the token is valid, then it generates a parse tree. If the token is valid by a parser includes a context-free grammar in it, and this is a token is an input string. So once the string was valid by a particular parser, it generates a parse tree. If not, it does not generate a parse tree. Once the token is received, the parser requires for the next token. As mentioned earlier, top-down parsing technique, the parse tree is created from top to bottom, starting from the root node to the leaf node. Bottom-up parser, the parser is created bottom to top, starting from the leaf node to the root node. Context-free grammar. Here, in context-free grammar, we have a set of terminals, set of non-terminals, set of production rules, and start symbol. These four are important. A finite set of terminals, a finite set of non-terminals, a finite set of production rule, and a finite and a start symbol. Here, E is a start symbol for this given production. E is a start symbol. E produces E plus T, E plus E, and E produces open braces E and close braces, and E produces ID. So E is a start symbol for the given grammar, and E produces E plus E. E produces open braces E and close braces. E produces an ID. So we have a set of production rules, and this E produces E plus E. It includes a terminal, and E produces E plus E open braces E and close braces. It includes a terminal, open braces and close braces of the terminal, and E produces ID. ID is a terminal. So it contains a set of terminals, and here E produces E plus E. So this E, capital E, are nothing but the non-terminals, and here E produces open braces E and close braces. Here capital E is a non-terminal. So a context-free grammar includes set of terminals, set of non-terminals, set of production rules, and a start symbol. Derivation. E produces E plus E. So E plus E is derived from E. So possibly I can replace E plus E in place of E. So to be able to do this, we have a production rule: E produces E plus E in a grammar. So this is E produces E plus E. and I can replace ID in place of this E, so that ID plus E, and as well one more, again I can possibly replace ID in place of E, so ID plus ID. This is a derivation based upon the given production rule. Coming to the leftmost derivation, rightmost derivation, here everything, this is the production which is given. E produces minus E produces minus open braces E close braces, E produces minus open braces E plus E close braces, E produces ID2. I can possibly replace ID in place of this E here. Can possibly replace ID in place of this E. So this is a leftmost E in the given production, and then I can possibly replace ID for this E also. So this is the leftmost derivation. I can replace right from the left hand side. Coming to the rightmost derivation, these things are same. Coming here, E plus E, I can replace ID in place of this E. This is in the right hand side, rightmost derivation, so that I can possibly replace the right hand side value of E as an ID and then go into the left hand side value. This is the rightmost derivation. So we will see the top-down parsing, try to find out the leftmost derivation of a given source program. And we'll see the bottom-up parsing, trying to find out the rightmost derivation of a given source program in a reverse order. Ambiguous. A grammar that produces more than one parse tree for a sentence is called as ambiguous grammar. So this is a string, ID plus ID, asterisk ID is a string. A grammar that produces more than one parse tree for a sentence. A sentence is nothing but a string which is given. So ID plus ID, asterisk ID here, and here also ID plus ID, asterisk ID. So this is a string that possibly generated by two parse tree, okay, based upon the given grammar, is called as ambiguous grammar. Here also, here we have a expression grammar, if expression then statement, if expression then statement, else statement. Here this is a string. When I look at here in this parse tree, if expression then, and this is statement, else statement. Again, I can replace this statement as if expression then statement. For this, I can replace this statement here. Statement produces if expression then statement, so that I am replacing this here for this statement, if expression then statement. Similarly, the first, again I can replace if expression then statement, and then I can replace the statement as if expression then statement, else statement. If I do so, I can possibly see, I can possibly get this string from this given parse tree for both the parse tree. So it is ambiguous. So we need to eliminate left recursion so that we can work with top-down parsing technique. So we need to work with the left recursion elimination. Top-down parsing technique cannot handle the left recursion grammar. So we need to convert the left recursion grammar into normal grammar. This is the left recursion, immediate left recursion representation. A produces A, alpha, beta. So A is the immediate left recursion. So I need to replace A. So A produces beta, A dash. And for this A dash, that represents this alpha and then A dash bar epsilon. This is the left recursive representation. A produces beta A dash, and this A dash produces this alpha A dash bar epsilon. This is an example. E produces C plus T by T. So this E is left recursive. So I need to eliminate this E. So E produces T E dash, and this E dash produces this plus T E dash bar epsilon. Similar for T produces T asterisk F bar F, and this produces T produces F T dash, and this T dash represents asterisk F T dash, this asterisk F T dash bar epsilon, and F produces ID by open braces and close braces. Here there is no left recursion, I can put the same. For the left factoring, we need to eliminate the left factoring in case if we have in the particular statement given. So the statement if expression then statement else statement, bar if expression then statement. I have two production rules here. I can possibly look at the left factoring. I can eliminate the left factoring in this by taking the common factors outside in the left hand side. This is an example. A produces alpha, beta 1, alpha, beta 2. So I have a alpha which is common in both the sides. So I can take this alpha in the left hand side. So alpha A produces alpha A dash. What is A dash? This A dash refers to the second component of the other elements which we have. A dash produces beta 1 and beta 2. So this is left factoring. I can take this alpha common element outside the given thing, and then I just represent A dash, and this A dash represents the other element, other component. This is called left factoring. Thank you.